Okay, class, so we're going to learn how to draw graph, which is your graph of half-life, and then next your graph of activation energy. So my tutorial question 5, is basically the past year question of 2011 and 2012. The decomposition of hydrogen peroxide is according to the following equation. The rate constant for the decomposition of 2.32 mole per dm cube hydrogen peroxide is 7.30 times 10 to the power of -4 per second. So first, you need to plot a graph based on the data in the table below. And from the table, second, determine the order. And next, determine the half-life of the reaction. Next is to calculate the concentration of hydrogen peroxide at time equal to 1600 seconds. And lastly, we need to calculate the percentage of hydrogen peroxide decomposed up to this time taken. So we've got 5 questions all together that is worth 13 marks. The minimum mark that you can get by drawing a graph is 10. Okay, so you need to be very careful when drawing your graph. So first, let us check out our information. So this is 2.32 mole per dm cube. Okay, so this must be at time equal to 0. This must be our A naught, which is our initial concentration. And per second, look back at your summary of graph. Per second, which order has the unit of per second, which is per time? That would be the first order. So we know that our graph must be the first order. But the question said that from the plot, okay, determine the order. So you must figure out, or you must draw your graph first, and then you'll be able to tell why your graph is the first order. So how are we going to determine that our graph is the first order? So we've got two options, which are, okay, the first one is by looking at the graph concentration versus time, or linear graph, or second, we can determine it by drawing our graph of half-life. Well, I'll always recommend my students to draw the half-life graph because it is really easy for you to differentiate the order by looking at the scale. So I'm gonna draw the graph by using half-life graph. Now look at a summary for the graph of half-life. So the y-axis must be the concentration of A, for example. So please add some notes. And the x-axis must be the time. So from our question, we already know that this is the first order, right? So our graph of half-life must be like this. It has a linear shape, and then your first half-life must be equal or nearer to your second half-life. So what I'm gonna show you is the graph that I've plotted already. So all the data given is already in your concentration together with your time. So you just plot your graph on your graph paper. So class, please make some notes. For chemistry, your graph must be more than, so your graph or the scale of the graph must be more than half of the page. And then second, the curve must touch at least half of the points. What I'm trying to say is that let's say that we've got 1, 2, 3, 4, 5, 6 points in our graph. So at least your curve must touch 3 of the points. Okay, so let's say for example 1, 2, 3. Okay, at least it must touch 1, 2, 3 points. So I'll start with the x-axis of 400 going to 3,200, and from my y-axis it going from 0 to 2.50. So look at my graph. Okay, I'll make it smaller. The graph is more than half of the page, so this is accepted in PSPM. So let's answer the question. I've already plotted the graph, and second, I need to determine the order, and third is to calculate the half-life. First, you need to calculate the concentration at the first half-life. Okay, so your A naught is 2.32, right? So divided it by 2, you've got 1.16 molar. So plot your concentration of 1.16. Is it? So this is the concentration at 1.16. Okay, and you must find the time given. So the time given is at here, that should be 960 seconds. Second is to find the concentration at the second half-life. So your first half-life, just divide your first half-life by 2. So you've got 1.16 divided by 2 to get 0.58 molar. Okay. So next, you need to draw your concentration on 1.58. So that would be, 0.58. So 0.58, this is the concentration at 0.58. You need to find the time. So the time will be 1840. Okay. So the number varies depending on the graph. So if you got, for example, 1880 for this time, then it should be fine because it all depends on your scale. So how are we going to determine, or how are we going to prove that this is a first order reaction? So you need to find the half-life. Okay, so our first half-life is at this point, right? 960. So at this scale, okay, this is our first half-life. So that would be 960 minus, what is the concentration at, what is the time at here? That would be 0. So the half-life is 960 seconds. Okay, so you've got 1 mark for that. For the second half-life, that would be going from this point to this point only. Okay, so this orange line, what is the time for it? Okay, that would be our second half-life, which would be 1840 minus, okay, the time at here is 960. So that would be 880 seconds. So now we're going to compare our first and second half-life. So we can say that from the graph, our first half-life is nearer to the value of our second half-life. Remember when I told you that, okay, the first half-life, okay, it must be equal or nearer to the value, because the value for first half-life is 960 seconds, which is nearer to the second half-life value, which is 880 seconds. So hence the order is first order reaction. So we are done with the first question. Third is to find the half-life from the plot. So you can't use this formula, okay, because this is from using formula. So in order to find your half-life, you must find the average of these two numbers. So your half-life would be the average of your first half-life divided by 2. Okay, just add up all your half-life together. So 960 plus 880 divided by 2, that would be 920 seconds. Okay, remember that we can't be using this formula ln 2 over k because we don't get it from the graph. The fourth question is to calculate the concentration of H2O2. So when the question asks you to calculate, means we have to use formula. So for the fourth question, we need to find RAT. So you already given T, which is 1600, and your A naught would be 2.32 molar. What about your K? Can we just use this value of K class? No. Okay. We need to find RK by using the graph. So let's compare your integrated rate equation with y equal to mx plus c. So we know that your gradient would be your negative k. So your m is equal to negative k. So how to find m, which is your gradient, is by using this formula. y1 minus y2 over x1 minus x2. So what you need to do first is to draw a big triangle on your graph. So for me, I've already drew it, and I've selected these 2 points as our x and y. So this is our point. So this 2.0 would be our y1, and this would be my y2, x1 and x2. So include this number into your gradient formula. Why you must draw a big triangle? It is so that your gradient will be more accurate. I don't want you to draw your triangle as small like this. No. Okay, just draw a big triangle. It won't affect your graph. Okay, so second is to find your gradient. So our y1, that would be 2.0 minus 1.0 divided by 200 minus 1200. So your gradient would be negative 1.1 times 10 to the power of minus 3. So for the third step is to compare your k, negative k with m. So your negative k is equal to negative. Okay, your gradient got negative on it. 1.1 times 10 to the power of minus 3. So your grade constant for the graph would be 1.1 times 10 to the power of minus 3. So now you've already find your k. So you can calculate your AT straight away. Okay, so basically just substitute your k. So the last step would be to find your AT, or to be more precise, you could say it as H2O2T. So ln H2O2T is equal to negative KT plus ln H2O2 not. So what is our gradient just now? That would be, okay, this one got negative, so put on negative in front of it. So 1.1 times 10 to the power of minus 3 times with the time given is 1600 second plus ln A naught, which is 2.32. So your H2O2 at a given time would be 0.0870 molar. Okay, so we are done with the fourth question. The last question is to calculate the percentage of H2O2 decomposed up to 1600 seconds. So this formula of percentage decomposition is not given in the lecture, so copy down it in your tutorial. So that would be A naught minus AT over A naught times 100%. So this is just a basic calculation, 2.32, and your AT, which you just calculate already before this, that would be 0.087. So for the last question, the percentage decomposition, there would be A naught 2.32 minus AT 0.087 divided by A naught 2.32 times 100%. So your percentage would be 96.25%. And one more thing, class, I forgot to tell you. You need to plot the concentration when the time is 1600 seconds. I don't know why they did that in this scheme. So that's the last step for your graph question, which worth 13 marks. So when the time is 1600, your concentration will be 0.7125 molar. We'll just plot it on the graph. We're not going to use it in any calculation because the question asks you to find the AT by using formula. So that's all for the graph of half-life.